I'm based in Oxford. I should say I spent a lot of my career at a place called the European Centre for Medium Range Weather Forecasts, helping to develop the forecast system there. It's a wonderful organisation based in the UK, but comprising member states from EU and non-EU countries in Europe. And it's a wonderful example about how we can achieve things by pooling resources. And I'm going to speak about that later on in the context of climate as well. The European Centre for Medium Range Weather Forecasts has been, for almost from the day it started, the single most successful and skillful weather prediction centre in the world. Anyway, I'm based in Oxford now with a so-called Royal Society research professorship. The Royal Society is the UK Academy of Science, and they pay my position to fund me to do research on climate, weather and climate. And if I can get the next slide to come up. Why isn't that working? There we go. So Roland-Jan asked me to talk about a paper which I wrote, which appeared in Nature a few weeks ago, which is about testing the reliability of climate models by studying them in very, very short range weather forecast mode, basically 6 hours, in fact. And this has had quite a, I would say, powerful, some research that we've done with the Met Office has proved that this is a very powerful technique for helping to validate models, but importantly for perhaps providing some sobering results which show that the amount of warming we may see as a result of our emissions of carbon dioxide may be even greater than we had previously thought. And I'm going to speak to that, but I need to really give some background to this talk, to this paper. So let me sort of step away from the paper for a moment and just give you some background. Over my career, I've debated, let's say, and argued a lot with climate skeptics in public as well as in private. So I just want to start with one argument which one sees from time to time from the climate skeptic community, that really, the so-called theory of global warming, as they call it, is just a gigantic weather forecast for a century and can have no value as a prediction. So this is one of the arguments people sometimes raise against the science of climate change. And I answer that by this very simple analogy, which is sometimes called an executive decision maker. It's a pendulum which, and I'll run the animation, which pendulum which oscillates around 4 magnets. And as a result of that, the oscillations are extremely irregular, and it's very hard to predict where the magnet will go from one moment to the next, which magnet it will go under. And you can think of this as an analogy with the weather. Think of those 4 magnets as different types of weather, maybe warm, dry, wet, and cold, or something like that. And the precise sequence of magnets is extremely hard to predict. And that's why weather forecasting, particularly going out to the long range, is very hard to predict in any precise way. Now, climate change, predicting climate change is not actually like sort of trying to extend that prediction to very long times. It's something slightly different. And the analogy I want to put out here is of trying to sort of tilt the magnet, tilt the whole pendulum. So let me do that in this analogy. So I slide this wedge under the pendulum, and the weather keeps evolving erratically, but you can see it's favoring one type of weather. The yellow magnet, if you like, becomes much more likely. And if you think of this yellow magnet as warm weather, then that's broadly speaking what's happening. So the wedge is related to obviously our emissions of carbon dioxide, and that's biasing the climate system very much towards certain types of weather. So that's really the basis of climate prediction. It's not a long-range weather forecast. It's a prediction about how the statistics of weather will change as we increase the concentration of carbon dioxide in the atmosphere. And that increase in carbon dioxide is sort of represented by the wedge. But actually, the problem is, and what makes climate change prediction difficult, what makes it difficult is not this chaotic movement, this very unpredictable movement from one magnet to another, but actually it's the question of how thick the wedge is. The wedge is providing the kind of forcing which is changing the statistics of weather. The problem is that this wedge is not just purely due to carbon dioxide increases. And I think this is something which is often not fully understood by the public, that the reason the climate change problem is a serious problem is actually not purely because of the increase in carbon dioxide. It's because of the consequences, if you like, of increasing carbon dioxide. It's because of the feedbacks or amplifications by other processes in the climate system. And I've highlighted some of them here. And one that, climate scientists have known about for probably, 100 years is what's called the water vapor feedback. So if you start to, so carbon dioxide is a greenhouse gas, which means it traps infrared heat that is escaping from the Earth. But water vapor, that's the gaseous form of water, also traps heat. And the issue is that as you increase the temperature due to our increases of carbon dioxide, you also increase the amount of water vapor in the atmosphere. And that's simply because as the atmosphere warms, it can hold more water vapor. I think we're all familiar on a cold, say, autumn day, autumn evening or autumn morning, where the air has cooled overnight. It can no longer hold the water vapor in the air and it condenses out into fog. And that's why we get fog, because the water vapor in the air it becomes too cool and it condenses out into little droplets of water, liquid water. But conversely, as the atmosphere warms, then water vapor increases and that amplifies the carbon dioxide signal. In fact, water vapor probably doubles the effect. If we have 1 degree of warming from carbon dioxide, it probably doubles to 2 degrees due to water vapor. And there are other feedbacks to do with ice, with methane, with the carbon cycle, which I don't have time to talk about in this talk. But one of the biggest feedbacks, but also the most uncertain of these feedbacks, are clouds. So just amplify it here, clouds. So clouds being the liquid or indeed ice, potentially ice crystal form of water. And the problem is that clouds can do one of two things, and it largely depends on how high up the cloud is. A low-level cloud will tend to block sunlight and cool the surface. A high-level cloud, the so-called cirrus clouds, which exist way up high in the atmosphere, little ice crystal clouds mainly, they do the opposite. They tend to trap heat. So depending on how high the cloud is, depends on whether it cools or warms the surface of the Earth. And the 64, I suppose you could say literally $64 trillion question about climate change is whether low-level clouds are decreasing or increasing, and whether high-level clouds are decreasing or increasing. And that determines whether clouds will amplify the climate change signal or somehow damp them. Now, to try to understand that problem, we have to use climate models. It's not something you can do on the back of an envelope calculation. You have to try to represent the atmosphere as comprehensively as possible using the laws of physics. So this is Newton's laws of motion, this is Max Planck's quantum theory, and this is the guy on the right is called Rudolf Clausius, who invented the concept of entropy, which underpins the laws of thermodynamics. And all these three are embedded in these climate models. I just had some animations. This is the real world from a series of satellites. We're looking down at the Earth in looking at this water vapor and how complex and turbulent it is. This is, again, an animation from a satellite of clouds bubbling up over the tropical Western Pacific. These are big thunderstorm clouds, and in fact, they spin up into two tropical cyclones. You can see the eye of the tropical cyclone. Very complex. So what I'm trying to get at here is very complex, turbulent behavior. This is one of our best climate models, again, looking at water. And it does, it on this global scale, it captures some of the complexity, some of the turbulent structure of the atmosphere reasonably well. if we look at, if we blow up over the tropical Western Pacific, like in the other satellite data, again, you can see things which certainly resemble the real world. Look, you can see those two cyclones spinning up in the climate model. But the whole thing looks a bit more like a kind of pointillist painting, I would say, rather than like the real world. Because ultimately, these climate models have finite grids. And the grids of current climate models, even the very best models, are maybe around 10 kilometers or so. And that means that all these individual cloud systems, like the thunderstorm clouds and so on, they can't be resolved properly with the proper laws of physics using those Max Planck laws and Isaac Newton laws, simply because the grid of the model is too coarse to do that. So all the white blotches in this last frame that you're looking at are using highly, highly simplified forms of clouds. They're called parametrizations. They're essentially sort of heuristic formulae for the cloud processes which can't be resolved by the climate model. So you're seeing something which is an approximation of reality, but it's certainly not reality. Okay, so what does that mean? So what it means is that when we talk about, and in particular, you often see in the media this notion of the scientific consensus. We all, scientists, climate scientists all agree about climate change. So what exactly are they agreeing about? And what they agree about is that certainly there is a very substantial threat of dangerous levels of climate change occurring with our emissions of carbon dioxide. However, there is no agreement about the specific amount or level of warming. And what we have agreement about is, in fact, that the correct way to frame the prediction problem in climate change is through this notion of a probability distribution. And that histogram I'm showing at the top of the figure is a kind of what has been for many years, I suppose, the consensus about what that probability distribution is. So let me just frame it. Let me just describe it a little bit more precisely. So along the horizontal axis, sorry, just to backtrack. So what this is an estimate of how much it will warm if we double the amount of carbon dioxide in the atmosphere from its pre-industrial amount of about 285 parts per million up to, say, 560, 570 parts per million. How much warming will we get? And you can see from the figure that there's a wide range of possible warmings, going from 1 degree at the lower end up to maybe 7 degrees at the upper end. Now, the bars indicate how likely that level of warming is. So you can see that the most likely level of warming is, say, around 2.5 degrees or so. But you see there's this kind of long tail which goes up to 7 degrees. And, substantial levels of probability at 4 or 5 degrees. The reason for this long tail is almost entirely because of this cloud problem. The fact that we don't know how much clouds will be amplifying or indeed damping. Some models do actually indicate a damping, but by far the majority of climate models indicated a warming. And the reason the climate models predict different things is because they all have their different sets of these heuristic parametrization formulae. So we can't really go back to the primitive laws of physics and say precisely what the warming will be arising from these the cloud feedbacks. Okay, so that's the first point, is to make that the scientific consensus is not an agreement about a specific level of warming, but about this probability distribution. Now, if you look at all the impacts of what climate change will do around the world, then certainly once we get above around 2 degrees, once we certainly get above the median of that distribution, we're in the level of dangerous, potentially even catastrophic climate change. Certainly when we get to around 4 degrees, we're talking about catastrophic levels of climate change for many parts of the world. One point I want to make here is that, just a sort of a slightly tangential point, is that saying something definite like climate change will unquestionably be catastrophic, or it will be lukewarm, as many of the climate skeptics like to say. All of the, or indeed it's a hoax, as President Trump, I think, once said. All these things where you say something very definite is actually inconsistent with the science. The science is very much more about estimating uncertainty through these types of distributions. Okay, now I want to come to the main point of this talk, which is that a number of the very latest generation of climate models, and these will feed into the new IPCC Intergovernmental Panel on Climate Change assessment report, which is due out next year, are actually suggesting climate sensitivities, this doubling this warming to a doubling of carbon dioxide, greater than 5 degrees. So 5 degrees is right at that tail. And many people have been questioning whether these models are correct, are the results believable? And these increased levels of warming have come about because of adjustments and changes made to the cloud parameterizations, to the representation of clouds in the models. And it's to do with a rather subtle thing to do with what's called supercooled water droplets versus ice crystal droplets. But the question is, are these results believable? And this is where my paper in Nature came up. Some years ago, I had made a proposal to test that we should test revisions in climate models just by simply doing, well, I say simply, it's not actually so simple, but by doing very short range weather forecasts. And there's a very simple way of saying this. If you change the clouds in your models, the way you represent clouds, things like your prediction of tomorrow's daily maximum temperature, will either improve if your cloud representations have improved, or they'll get worse if your cloud representations get worse. So by looking at a very large sample of short-range weather forecasts, we can look to see whether the changes you've made in the cloud, in the climate model cloud representations, are improving weather forecasts or not. Now that may sound easy to, well, it's easy to say, but it's actually an extremely difficult thing to do in practice, because we're talking about rather small and subtle changes. And also many climate models actually don't have the capability of being run in weather forecast mode, because the reason is because it's quite a complicated procedure to be able to ingest observations directly into a model to create a set of initial conditions. So all I'm saying is that the idea is fairly simple, but putting it into practice is quite complex. But one climate model which is, well, in fact, one of the very few in the world which is run both in weather forecast mode and climate mode is the UK Met Office Hadley Centre model. So the UK Hadley Centre model was actually one of them that had this increased climate sensitivity of 5 degrees. So a scientist called Keith Williams at the Met Office did these tests, and indeed it showed that the revisions they'd made to the cloud, which led to this increased 5-degree level of warming, which really is quite, that's a dangerously worrying level of warming, had improved weather forecasts on the very short timescales of 6 hours. So the point about this News and Views article was to say this really does add some major level of credibility to these projections. And so it really means we have to double down in our efforts to cut carbon. I just thought I would if I could spend 5 or 10 minutes just talking about the importance of climate models and the direction in which the developments are going.
Yes, please.
Yeah, okay. Have I got just 5 minutes more? Yes, okay. So
you got about 15 minutes, so
oh, I have 15 minutes. Oh, okay, that's even better. Okay, so let me just say, why are climate models important? Because sometimes I'm going to talk about, proposals for developing climate models, and some people say, oh, well, it's just, it's just bigger toys for the boys, if you like. But it's certainly true that climate models are an important tool for understanding the climate system, and understanding is important, of course. But they have some extremely relevant policy. They're extremely relevant for a number of policy implications. So I just want to highlight some of those policy implications. So mitigation is really about implementing emissions cuts, and Here, I would say there is an important policy question which requires much more accurate climate models than we currently have. And that is the following, that emissions cuts, even if we implement the type of very stringent emissions cuts that many countries are thinking about 2050, getting to net zero by 2050, they do rely on, in some ways, of sucking CO2 out of the air at a later date. Maybe we plant trees which come into maturity by mid-century, or maybe we have the technology that can actually directly suck out CO2. Now, there is an important technical question, well, no, not technical, but policy question here, which is that if we start passing significant tipping points, things like the melting of Greenland, melting of the Greenland ice, or rainforests no longer becoming sustainable due to changes in rainfall amounts, that sort of thing, then this negative emissions technology will be completely ineffective, later in the century. The whole point of a tipping point is that once you pass it, you can't get back to where you were before. So putting in negative emissions could be ineffective. And so we really have to understand whether these tipping points exist or not. And current climate models are just too coarse in resolution to be able to do that. We don't know. Another important reason for accurate climate models is climate adaptation, making society more resilient to the changes in extremes of weather that are associated with climate change. And there we really have to know not just about kind of global mean temperatures and things like that, but what climate change will mean for specific countries and regions of the world in terms of things like heat waves, which are too hot for the human body to literally survive in, or storms that have unprecedented strength in terms of winds and storm surge and rainfall, or long-term drought, all these things, which are very regionally specific. We need accurate climate models to be certain about what is happening at the regional scale, because that will inform the climate adaptation decisions. So if we're going to make good climate adaptation decisions, we need accurate climate models. Geoengineering is something which is sometimes raised as a possible plan B if we can't agree to cut emissions globally, which is to, for example, spray the stratosphere with these small sulfuric acid droplets, which turn into sulfate aerosols, which then block sunlight. But there are some big science questions around this, which is that we don't really know what we're doing at the moment, at least with such an experiment. Could we inadvertently start diverting the monsoons from where they are currently? Could we end up stopping the moisture supply into the rainforests? All these things are possible because geoengineering is not directly offsetting the increase in carbon dioxide. It's changing a problem in the infrared part of the spectrum by reducing the incoming solar sunlight in the visible or ultraviolet part of the spectrum. So these are really big questions which can't be answered unless we have accurate and reliable climate models. And then, of course, these models are important for early warning on timescales, shorter than climate, on timescales of days or weeks or seasons ahead. And I would argue that this is actually an important part of the adaptation program anyway, helping people, particularly in the developing world, to become more resilient to extremes of weather. One way is to certainly help make the predictions of extreme weather more reliable so people can take appropriate protective action. It's just salutary to remember that in the 1970s, before we had any type of weather forecast model, tropical cyclones would kill hundreds of over 100,000 people, countries like Bangladesh. So it's because we have much more accurate early warning systems that the deaths due to these extreme weather events have been reduced so substantially. But we need to go much further, given the increased intensity that we can expect from these events with climate change. And then, of course, the whole question of attribution is one, certainly in the media, is a kind of important question. The media, when we get an extreme event, then people always ask how much more, was that caused by climate change? And in a way, that's an important question, because underpinning that question is how much more likely can we expect that type of extreme event to become in the future? And again, these types of questions cannot be answered other than with accurate climate models. So as mentioned, I worked for the European Weather Centre, and this is over 10 years, well, about 10 years ago now, I wrote an article in Physics World saying we need to pool our human and computational resources in Europe and create something like a CERN for climate change, where we create the types of climate models that could not be created at the national level. And well, some years ago, about maybe 4 years ago, I held a meeting with some of the leading climate modeling groups at the Royal Society, and we put in a proposal to what was then the EU flagship the flagship program for a kind of CERN for climate change. The program actually, the whole flagship program was cancelled, so this never really got through to fruition. However, it has, I think, the proposal has has stayed in the system, and I'm very pleased to see that in the new part of the EU Green Deal, there's a program called Destination Earth, and it says here that the objective. So this is from the European Commission's web pages. The objective of Destination Earth is indeed to develop a very high precision, high resolution, that is to say, digital model of the Earth. And through this Destination Earth project, the Commission is promoting this concept of digital twins, they're called, which is basically, climate models. And this will actually, I think, I'm hopeful that this will actually sort of sow the seeds for at least a virtual kind of CERN for climate change, where we're developing new types of climate models with unprecedented levels of detail, doing things at the European level which can't be done at the national level, pooling human and computing resources. For example, the Euro HPC supercomputer is a consortium of supercomputing nations with supercomputing capability. And we are rapidly approaching the exascale, the era of exascale computing, 10 to the 18 floating point operations per second, extraordinary levels of computing speed. But this is what is needed to provide these very high resolution climate models. And, these models will link directly to impact and application models then, which will directly inform on policy in things like, flooding, hydrology, in agriculture, in food production, in health, for example, the emergence of disease, which is weather related, and other types of application. So I'm just going to conclude, and I've got sort of two slides because I feel they're two separate sides to my talk. I wanted to make the point that how bad climate change will get does depend critically on it's not just actually on our CO2 concentrations, but in aspects of the climate system which we don't fully yet understand. And I'm trying to argue that one of the single most important ones of those is actually to do with clouds. Clouds seem very mundane objects, but in some ways they hold. So next time you look at a cloud, just think it holds the fate for humanity. Humanity will literally live or die by how clouds adjust to increasing levels of carbon dioxide concentration. I really can't put it more bleakly or bluntly than that. And some of the latest generation of climate models, the ones that will feed into the next IPCC assessment report, which have revised representations of cloud, do suggest a significantly greater level of warming than previously thought. But again, I make the important point that these representations of cloud are rather simplified ones. They're not based on those direct laws of physics, but with rather heuristic formulae. And so you can question whether they are right or not. However, there is support for those latest results coming from the fact that weather forecasts are actually improved with these new cloud representations. So I think we do have to take the high level, the possibility that clouds will be amplifying significantly the climate change signal. We have to take that very seriously indeed. And then my second conclusion is that really we do need to develop much more accurate models. For example, where the clouds are represented explicitly by those laws of physics that I showed. This will need us to get down to much higher resolution, so the grid cells going down from 10 kilometers to 1 kilometer. And that's a major increase in computational performance needed. It's only possible with dedicated next generation exascale computing. But more than that, we need to kind of pool our effort. We do need some kind of CERN for climate change where human and computational resources are pooled. That's the only way to really proceed as rapidly as possible. And certainly answers are needed rapidly in this problem. And so if anyone listening has any influence in the development of the something like the Destination Earth program, which is part of the EU Green Deal, I very strongly urge you to try to support it as strongly as you can, because I think this is probably our biggest opportunity to do something in a transformational way on our ability to model and predict, indeed, climate change, both globally and regionally. Thank you very much, Sirpa. I think I finished at this stage.